Okay, so first we're going to cover BIOT-Savart's law. The very top one is probably not necessary. If you want to, you can go ahead and write it down um, in the case that they test it, but it's most likely not going to be tested. Okay, the next one. This one is very necessary. It's the equation to calculate the magnetic field of a wire. I'm sure all of you have seen this before. It's like in the expert TA, it was in a lot of homework. Everyone probably knows how to use this already, right? If you don't know how to use it, leave a comment and we'll get back to it later. But I'm gonna move on for now. We're gonna speed through this. The next equation, can y'all see my mouse?
Yeah, we can see your mouse.
Okay, cool. So next equation is the force between two wires. This one's probably not necessary, but this one might as well write it down because you actually know how to use the equation. Right, this one's a bit weird to use, but this one you're just plugging in, right? Current in the first conductor, current in the second one. Just write it down just in case if they have it. They'll give you all the variables necessary to solve it, so you'll be fine using it. And then the last equation, this one was in the practice exam where you have like a ring, right? And then you have there's a distance x and the ring has a radius a. You just plug and chug. It's quite simple. BIOT-Savart is just plug and chug. There's no theory or no theory that we need to know. Okay, so I'm gonna move on now. If any of you have any questions, just leave it in the chat. Okay, so the next topic they cover is Ampere's law. This one's probably not necessarily the top equation because this is like the derivation of Ampere's law. If you look at it, it's very similar to Gauss's law, and that's because I enclosed is similar to like the charge enclosed, but we're multiplying by the magnetic constant here. And the dl just means the length that we're integrating around. So what that means is, like after this thing is derived, the magnetic field of a solenoid will be equal to the mu naught ni. Yeah, mu naught ni, where n is equal to the big N divided by the length. So does everyone understand how to use the equation for the magnetic field of a solenoid? Tanner has a question in the chat. Does Ampere's law only work with symmetric stuff? The answer is you can technically use Ampere's law for anything, but it's just a lot easier to use if it's symmetric. Like if you just have one straight wire, then it's a lot easier to use because the line integral that you're taking is just constant. But like if you have a really complex thing, you can't just like take it. You can't just remove the integral. You have to actually take the integral. But if it's symmetric, you can remove the integral. That's the difference. Okay, yeah, what Kevin said. Okay, and there's actually one more derivation for Ampere's law, and that's like for cylinders, but I'm not going to cover it here because it's probably not going to be tested. So,
sorry.
Okay. Okay, so now we're moving straight on to chapter 29, Faraday's law. These three chapters are all pretty easy. It's just like a couple equations. So first thing to know about Faraday's law is how to calculate flux, right? Which is the omega b flux, and that's equal to the magnetic field dot product A, which in reality just probably means B times A times cosine theta between the B and A vectors. So I'm gonna pull up a whiteboard real quick just to do like a quick review. So once again, if we have like a, let me draw that better. If we all have like a plane here, or no, like a square wire here, okay? And we have a magnetic field going through this way. The magnetic field is pointing due right. The area vector is actually going to be pointing this way. Most people think that the area vector might be pointing this way, but that's actually not where area points. Area vector points this way, or it can point this way. So the theta between B and the area vector. So B dot A is going to be BA cosine. I'm just going to define this thing right here as theta, the angle between the magnetic field and the area. Okay. Back to the PowerPoint. Oops. Okay. And then the next step after that is Faraday's law itself. The EMF is equal to the derivative of the flux with respect to time. And then there's also a times in there for like the number of turns. And this thing is also could be simplified to just the change in flux and change in time. So you don't even need to do derivatives if they don't give you something to derive. And also EMF is also equal to B times the length times velocity. That's if they're given velocity. And let's say you have like a box moving into a magnetic field. You're given its velocity, you're given its length, right? So then in this case, the EMF is equal to B L V. All right. If I'm going too fast, just say something in the chat.
Wait, I'm
How do we
sorry.
know which
Can you
LT
go back
is?
real quick to the whiteboard of what you just wrote?
Uh-huh.
How do you know which LT is? Is it
Okay, I'm good now. Sorry, I got out earlier.
L has to be the this length. It can't be this length.
okay?
Yeah, because this is the length that's changing with respect to velocity. Just like think about it that way.
Okay. So it's like you're taking derivative, basically.
Yeah, you can think about it that way.
Wait, I'm sorry. What is the scenario again?
So you have a loop of wire. This is your loop of wire, and it's moving at velocity v into this magnetic field B. And right now it's not in a magnetic field. So the EMF as it moves into the field is equal to BLV.
Okay, thank you so much.
And there's a way to derive it. It's actually pretty easy, but I won't get into it unless y'all are curious. Okay, so back to the PowerPoint. Okay, so here I wrote at the bottom, probably not necessary. This E actually refers to electric field. So if y'all did the expert TA, the last like 2 questions for this expert TA, you have to find the electric field. So electric field is just EMF divided by 2 pi r in most cases. And r is just the distance. So I'm just gonna share my screen again. So once again, I wrote there E is equal to EMF divided by 2 pi r. And let's just say that like I have a magnetic field confined here. And I want to find the electric field at a radius r out here. Right? Well, first of all, in order for there to be an electric field, there has to be an EMF, right? So that means there has to be some some BA change in time, some change in B or some change in A over time. Okay.
Hey, Steven, can you let Eric into the?
Yeah, I just did. Sorry.
Okay.
I'm not checking my Zoom.
Okay.
How do I just make them automatic join?
Just check more often.
Okay, it's so annoying.
I think you
Okay.
can click next to participants and disable waiting room or something like that.
Okay, let me try that. I cannot figure out Zoom. Oh my god.
Okay. Well, anyways, so this top part is just the EMF. So there has to be some changing magnetic field in here in order for there to be an electric field out here. Okay. And to calculate the electric field, we'll just do the EMF inside at the inside divided by 2 pi r. Makes sense, we all good? And I'm not doing any derivations this time, so you just have to take my word for it. Okay. Okay, now we'll talk about Lenz's law. So Lenz's law is a super confusing concept. Took me a while to get the hang of it as well. But maybe this live demonstration will help you a bit. So let's say the question is, I have a magnetic field going through this loop of wire, okay? B, and this B is increasing in magnitude, okay? So what direction is the current flowing in this loop of wire? So first of all, I want y'all to type in the chat and tell me what direction you think it's going initially, so I can judge how well y'all already know Lenz's law. So just say clockwise or counterclockwise in the chat or out loud. I'll give people a bit more time to answer. Oh yeah, and we're gonna pretend we're viewing it from above, okay? So we're looking down at it. And yes, the answer is counterclockwise. Yes, because it's opposing the change in flux, exactly. Okay, now I'm gonna give you a slightly more stranger one. Okay, and B is decreasing. So tell me, what direction is the current flowing? Yeah, it's counterclockwise still. Ray, why are you so confused? You got it right. Oh, just kidding.
Wait, so try recording this one now. You can.
It's fine. Whatever, just do everything. Just record everything.
'Cause I'm not sure if it's actually recording the screen.
No, you are.
Okay.
Okay. I think everyone knows this pretty well. Does anyone want me to go over it?
Yeah,
Okay,
could you
just
over
go
it?
over it.
Okay, sure. Okay, so once again, we'll look at this example where the B is decreasing, okay? So how you can think about this is first let's look at the flux. So the flux area, it doesn't matter what direction area is going, flux will just probably just depend on B. Just think about it that way. The direction of B, okay? So the flux, initially, the flux is, let's just say it's this big, okay? And we know B is decreasing. So as time goes on, flux gets smaller. Maybe it's like this big, right? And then flux gets smaller as time goes on, right? So if you think about it this way, how do we put our thumb in the direction where we have to add on, right? So we need to add on to these to make it more like the initial position, okay? So we need to add on to these ones. So we point our thumb in that direction where we need to add, all right? So we need to add upwards in order for it to be back to its initial position, right? So if we point our thumb upwards, now our hands curl this way, it's counterclockwise. And this is like a bit weird to think about at first, but it's like a pretty standardized way of thinking about it. Because the formal definition of Lenz's law is that the magnetic field produced by the current counteracts the change in flux, right? So in this case, the flux is changing to be smaller, right? So we need to counteract this change, right? So this change in flux is going down. From here to here, it's going down, right? From here to here, it's going down, the change in flux. So in order to counteract that, we need to put our thumbs up. Okay, so let's think about another example. Let me read the chat real quick. If the arrows were going down and B was decreasing, if B was decreasing, oops, that's not B. If B is decreasing, then it would be clockwise, yes. If B is decreasing and the arrows are going down, it will be clockwise because the change in flux is upwards, so we need to counteract that by going down. Okay, so let's just do another example just to be certain, because this stuff is kind of strange to think about. Okay, so this is going into the page. This loop of wire is going to be going into the page, okay? I mean, this loop of wire is moving into a field that's going to the page, is what I meant to say. All right, so let's analyze the changes in flux as it goes into the page. So, I mean, as it goes into the field. So before it enters the field, right, there's no flux. As it enters the field, half of its area is taken up here. So I'm going to say there's a flux going into the page, okay? And let's say it's fully immersed into the field here. Okay, let's just say it's fully immersed in the field. Now there's a huge flux in the page, right, as it moves in. So how do we counteract this change? So to go from here to here, the change is there's more going into the page, and now there's even more going into the page. So how do we counteract it? We go out of the page with our thumb, right? And our fingers will curl this way. That would be counterclockwise. If you already have your own way of thinking about it and it works, just go with your way, because I mean, it's just really weird to think about. But hopefully this makes sense. Does anyone need me to do another example?
There was one expert TA with a circuit, and I was kind of confused on how to approach it.
Was it this one? Lenz's law, right?
I think so. It was an RL circuit.
Oh, RL circuit. Oh yeah, we'll cover those later.
Oh, okay.
Okay, yeah. So in that case, I'll move on so we have more time to cover the other ones. These are supposedly the easier chapters. All right, so now we'll cover inductance. So yeah, that's already chapter 29 finished. Like, Faraday's law is not too hard. If you have any questions, just leave it in the chat, and Kevin will start teaching now, and I'll answer your questions. Oh, really? Okay, sure. Okay, well, for inductance, these are the equations for mutual inductance. Literally, all you need to know is just write these equations down, and then the question will say, like, I give you the number of turns in coil 2. I give you the flux change in
still on the
coil 2.
whiteboard.
Yeah, they'll give you everything. Wait, what was that?
You're still on the whiteboard.
Oh, really? Okay, whoops. Let me just... What the? All right, so this is the equation for mutual inductance. Questions will literally give you everything, okay? They'll give you N2, I1. They'll probably give you like how to calculate the magnetic flux, but you already know, how to calculate magnetic flux. You just spent an entire unit covering it. So. What was that?
I think Connie's mic was just on.
Okay. So this is pretty simple. It's literally just plug and chug, okay? Now self-inductance, there's an equation for it, for L. So just know this equation. Yeah, so like basically the reason I included that slide, I don't think it's terribly important, but it is pretty interesting to see, like, this is the equation that tells you what the inductance of an inductor is. It's really analogous to capacitor. So like the inductance is similar to how a capacitor has a capacitance. And that's what self-inductance really is. And that's why I wanted to include it. But you don't really need to know this stuff. This equation? Yeah. This equation for L? Yeah, that's the equation for, or it's analogous to capacitance. No, but this equation for L is necessary. This equation for L might be tested. Yeah. I mean, it will be tested. You might, you might be used to seeing it in a different format, though. Here, let me share my whiteboard again. Okay. We might be used to seeing L Okay, so what Kevin had was the general equation for any shape. 1 second, let me get my formula sheet out. They will most likely test the L of a solenoid, okay? 99% of the time they'll test you the L of a solenoid, okay? So in that case, there's the equation for the L of a solenoid. It's just gonna be the like derived version of the other equation. But I'm not gonna go through the derivations. I'll just give it to you. Just take my word for it. I'm trying to find it. Oh, there it is. It's pi mu naught n squared, like big N squared. So like the total number of turns in the solenoid, r squared divided by length of the solenoid. And I derived this from the equation that Kevin had on his sheet. Is this the equation you had?
L is equal to divided by.
Oh, whoops.
Oh yeah.
There's no D.
Yeah.
I just derived this from Kevin's equation, but just know this one. This one probably won't be tested. But I mean, you could have it on there anyways. You know how to calculate flux, so. So yeah, this is the L of a solenoid. And then the voltage or EMF is equal to L times the rate of change of the current, right? They might they'll probably just give you something like this. So let me share my screen again. Let me share my whiteboard again. So they'll ask you like, what is the EMF if the I goes from like 0 to like 15 amps in like 10 seconds, right? And they give you like L is equal to 5 henries or something. What you'll do is just do 5 times change in current divided by change in time, right? Does that make sense? Because the equation is L di dt. So, okay, let's move on. Wait, what? Okay, the energy in the inductor, just know 1/2 Li squared. Kevin covered up the calculus because it might just be confusing. Just don't worry about the calculus. Energy stored in the inductor, 1/2 Li squared. And then the magnetic energy density, once again, it's just the equation. If they ask for it, you have the equation for it. All right, now let's talk about the RL circuit. So the time constant in the LR circuit, RL circuit is this. Similar to how we had a time constant in the, well, what else did we have a time constant? I forgot. There was a time constant in the charging capacitors, I think.
Capacitors,
Yeah.
RC circuit.
RC circuit? Okay, well, yes. Yeah, RC circuits.
Wait, you're talking about the RL circuit.
Yeah. Okay. Yeah, and similar how in RC circuits we have like the equation for how I changes with time. This thing has the same thing with the equation I changes with time through this equation. It's just plug and chug. I starts at 0 when it's charging up. And when time goes to infinity, it reaches E over R. And then discharging, this is the equation. I naught is the initial I value. So a lot of this work depends on you having a good background knowledge of how to calculate I, like, you know, Ohm's law. I is equal to V divided by R. So have a good background. I'm not going to cover many practice problems, but does that answer your question, whoever had the question earlier? Or should I do more practice problems over this? Oh, Z and inductive reactance, that's later. Because that's in AC circuits. Right now, we're just talking about the RL circuit discharging. So like, let me just show you what this thing will look like. So what this type of problem might look like, RL circuit, is you have a resistor, you have an inductor, and then it's like discharging, or yeah, like it's discharging, okay? And you want to find like I at t equals like 4 seconds or something. And you just plug in and chug. Tanner, what you're talking about is something that looks like this, where you have an AC current. In that case, then you'll have to use the Z and the reactive inductance thingy. So that's in the future unit that Kevin will cover.
So there was a problem on expert T where it asked you to find the direction of the current at a certain time. Do you know how you would do that for an RL circuit?
Oh yeah. So I believe the question was like this.
Yeah.
Something like this. The direction of a circuit, this is the positive end, this is the negative end. The current flows out of the positive end and into the negative end.
Okay, thank you.
This actually has nothing to do with RL circuits, just batteries.
And then you do right-hand rule?
You don't need to do right-hand rule. This is just counterclockwise.
Oh, okay. Thank you.
Okay. Any more questions? All right. See, I'm gonna. Okay. And then LC circuits, inductor, capacitor. Similarly, we have an equation for the charge in the capacitor at a given time. So this Q equals that. And W, the angular frequency, is equal to 1 over LC square rooted. And I mean, applying this is pretty simple. Oh yeah, the phase angle or phi, it just depends on the initial condition. Like, let me give you an example of how we would use phi real quick. What time is it?
9:30.
Okay, we have time. So like, let's say that at time equals 0, the charge on the capacitor is max charge Q, okay? And I'll just draw this out just so that we can visualize it, what's going on, okay? So at time equals 0, max, the charge in the capacitor is Q. Okay, so what does that mean for the equation? Q is equal to Q cosine WT plus phase angle. Okay, and this Q here is just means the max Q. So we're saying at time equals 0, the Q is the max Q. Okay, so what does that mean? That means Q is equal to Q cosine 0 plus phi, right? So that means phi has to be equal to 0, right? So we actually don't have a phase angle here. So that will be like a example of how we calculate phi, the phase angle. The phase angle it depends on the initial conditions here. So does anyone have any questions about how I calculate the phase angle? So normally you don't need to worry about the phase angle. Okay, and then like in the future, like let's say what is the Q at time equals like 5. Literally just plug in, you know, Q is equal to Q cosine W times 5. And you have calculate W elsewhere. W is equal to square root 1 over LC, right? It's just simple equation stuff. Okay, moving on. The energy of an LC circuit. So you've seen the magnetic energy before, 1/2 Li squared. That's just the energy inside of the solenoid, right? And you've seen electrical energy before. This was a while back, but you actually know this equation, believe it or not. It was like literally our like 2nd or 3rd unit we've covered. It was a long time ago. But this is the electrical energy inside of an electric field. because what's happening with energy, I'm gonna share my whiteboard again. Basically what's happening is that, let's say initially, if all the charge was in the capacitors, all the energy is actually in the electric field between the capacitor, and this thing has no electric field. This thing has nothing. This thing is broke. Okay. So as the capacitor discharges and the Q leaves and becomes I, so now at this point in time, I is max and Q is broke, Q 0. All the energy is stored in the inductor. And the next slide will actually go into this more in depth, but basically what we can derive from this, it's like an oscillation. Remember how we had like a spring, we had a box in mechanics, right? The max energy in this oscillation was, let's say it was displaced a distance x. The max energy in this oscillation is just going to be 1/2 k delta x squared. The max amount it was displaced in the beginning squared. That's the max energy. And then the energy at any point in time afterwards is going to be the sum of the potential energy and the kinetic energy. The potential energy in the spring, in the elastic. Okay, so that's going to be our mechanics analog. So similar in this case, in our electrical analog, it's like an oscillation. We have our max energy. Let me just erase this thing down here. We have our max energy, which is just equal to the initial energy in the capacitor's field, right? So it will be 1/2 1/c. I forgot the equation. And then Q squared, I think, yeah. Right, that'll just be the max energy. They might ask for max energy in a question or something. This is how you'll calculate it. This is just the initial charge in the capacitor. And then I don't think they'll test the oscillations themselves, but if they say like, what is the energy in the what's it called, L in the inductor at time equals 3 or something. Well, the energy in the inductor is going to be the max energy minus the energy remaining in the capacitor. This is like the oscillations. Okay, does that make sense? I'm gonna move on now. We gotta move on. Just think about a spring from back in mechanics. Okay, so yeah, this diagram shows the oscillations. So initially we see that the capacitor is fully charged, then the capacitor discharges and all the energy is in the inductor and the current is max. So here the charge is max, now the current is max. Then it keeps flowing and now charge is max again in the capacitor, right? And then it goes back and then the charge is 0 in the capacitor and then the current is maximal again. So it's just an oscillation that looks like this. But you can review this slide by yourself later. Okay. Kevin?
Mute yourself and turn off your sound.
Okay. Hello, can everyone hear me? Oh my. Turn for sound. All right. Actually, before we move on to, I think we're moving on to chapter 31 now. Oh, wait, I need to share my screen. Okay. Oh, wait. Okay. So, chapter 31 is all about AC circuits. So what Stephen was talking about previously, all the equations were DC circuits. But once you have an AC circuit, a lot of stuff changes. Now, first of all, what exactly is an AC circuit? Well, basically all it means is that you're changing the voltage sinusoidally, okay? And that also means that you're changing the current sinusoidally. Okay, and what you have here is voltage is equal to the maximum voltage amplitude times cosine times of omega t, and omega is just the driving frequency, which is what the question will always give you. So the driving frequency of the AC generator. Okay, that's what AC circuit is. All it means is that the voltage is oscillating. Now, there are two very important things that you have to know with AC circuits. Is the root mean square values of the current and voltage. So just memorize these two equations. They're on your formula sheets. So the reason why this is so important is because, like, basically if they give you a question on the test and it doesn't specify if it's the RMS value or if it's the, the voltage definition of the sine definition, you automatically assume that it's the RMS value. And the reason is because you can't really say that, the voltage of a AC circuit is 120 volts because it's oscillating sinusoidally. So you have to be referring to the RMS value. Okay. Any questions on this?
So regarding RMS, that's only going to be whenever the test asks about anything related to AC circuits, right? Otherwise,
Yes.
anything else is going to be just straight up normal voltage, right?
Right. Yeah. RMS only applies for things that are oscillating sinusoidally. Okay. So here, all right, so basically with the AC circuit, you can add components to the AC circuit. So you can add a resistor to it, you can add an inductor to it, you can add a capacitor to it, you can add all three to it. The main thing of the AC circuit is Ohm's law. It follows Ohm's law, but in a slightly different way, but essentially it is Ohm's law, okay? So first of all, let's consider the case of a resistor. How do I pull up a whiteboard? Actually, let me, I got you. No, I got it. Can everyone see this whiteboard? Do you see the whiteboard? Yes. Okay. So let's say that we have a AC circuit and we have a resistor attached to it, and that's it. Basically, all that you have to know about this AC circuit is that it follows V is equal to IR, okay, where R is the resistance of the resistor, and V is the maximum voltage, or it could also represent, actually it's the maximum voltage, it's the voltage amplitude, okay, and I is also the voltage, the current amplitude. So that follows Ohm's law. We're all familiar with this. Now let me draw a different clear. If I draw, okay, now let's talk about an inductive load. So inductive load, all that means is that you're attaching a inductor to the AC circuit. In the inductive load, you also have V equals IR, but it's a bit different form. Instead of calling it the resistance, I'm going to call it the inductive resistance or something like that. What's it called again, Steven?
Huh?
It's called
I have no idea.
Inductive resistance.
Inductive reactance.
Yeah, inductive reactance. Very good. So yeah, it's called the inductive reactance, and its formula is given by if you look at the screen, the formula for inductive reactance is the formula for inductive reactance is the driving frequency times the inductance, that's the name. Yes. So XL is equal to, so it's just a different definition, but this has the exact same purpose as a resistor. Okay, and also the other formula you have to know is if you instead have a capacitive load, in other words, you just have a capacitor, it's the exact same thing. You have V equals I x C, but this is the defined as 1 over omega times the capacitance. Okay, so these terms should be on your formula sheet. And yeah, they're basically used in any question that you have like a AC. So instead of a DC voltage, you have an AC voltage connected with a capacitor, resistor, or inductor. Bruh. So funny.
Nothing.
Why are you laughing?
Nothing.
Okay. So, all right. Anyone have any questions about this? Real quick, I do want to mention, wait, hold on, look at my screen. Am I showing the PowerPoint slide?
No,
wait,
you're not.
how do I have to change.
Just mouse your to the top.
I know. Oh wait, do you see my screen now? Okay,
Yes.
cool. One thing I note, I put on the bottom is you see V is equal to big V. Big V again stands for the amplitude of the voltage, so the maximum amplitude. And this formula looks really similar to, if I can go back a slide.
Ray asked a question.
Oh wait, how do I look at the chat? Oh, there it is. What? I can't see the chat.
Press more.
I did. Oh, there it is. It's just very slow. Oh my gosh, that's annoying.
Oh my god, do you want me to read the question to you?
Come on.
So both XL and XC are basically resistors in AC circuits.
Yes. Or the resistance.
Yeah, they're the resistances.
Yeah. So yeah, that's how I remember it. It's not technically the resistance, but it follows the same mathematical formula. Formula as it. So I was talking about this voltage right here. So if you look at the voltage of a inductor or of an inductor connected to a AC circuit, if you look at how the voltage oscillates over time, you see that it looks really similar to how this voltage looks. And this is the voltage of the original AC generator, okay? And this is also, by the way, this is also the exact same equation as the current. And you basically replace all instances of V with I, and that's the current equation as well. What this means is that, and also there's a plus phi, and it doesn't, phi is supposed to be plus 90, okay? What this means is that the voltage of a inductor leads the current by 90 degrees, okay? And on the other hand, the voltage of a capacitor lags the current by 90 degrees, okay? And I'll show you why this is important in the next slide. Actually, I'll show you right now. Basically, if you look at the right, there's a phasor diagram. Phasor diagrams are, they look really complicated, but actually they're pretty simple. Basically, all you have to see is, okay, the middle, do you see my mouse?
Yeah, we can see your mouse.
Okay, this middle vector right here,
I don't think you need to.
phasor.
I don't think phasors is necessary.
Okay, I will skip phasors. But anyways, you can use, basically, the reason I was bringing it up is because you see that this one is leading, one of the vectors is leading the current, and one of the vectors is lagging the current, and that corresponds with this 90 degrees lead and 90 degrees lag. But anyways, you can use that to calculate impedance. Impedance Z is equal to this. And again, it's Ohm's law, right? You have V is equal to IR, V equals IZ in this case. Z is the impedance, all right? So just memorize these equations. And this last equation on the bottom is about the phase angle. So what the phase angle means is, okay, if you look at, okay, I do need to explain the phase diagram, okay? If you look at this phase diagram, basically the phase angle is an angle between the central vector. And the central vector is just a current vector that goes around in a circle. It's the angle between that one and the true voltage vector, okay? And the true voltage vector is just the sum of all three of these voltage vectors right here. So the voltage caused by the inductor, the voltage caused by the capacitor, and the voltage caused by the resistor. That's what the phase angle is. If you get a positive phase angle, that means that it's leading. If you get a negative phase angle, that means it's lagging behind. Okay. All right, so now let's apply this to a quick practice problem. So we have this series RLC circuit, okay? Well, first of all, before I go on, does anyone have any questions about these equations?
Yeah, I need to clarify something. So go back, Kevin, go back a slide.
Uh-huh.
So when we say leads current and lags current, that means the voltage leads the currents by 90 degrees for the inductor. We could also say that the current lags the voltage by 90 degrees. So it depends on the reference. Like, are you saying that the current is lagging the voltage or the voltage is lagging the current? So remember, in inductor, how I think about it is the current lags the voltage, or you could think about it how it's on the slide, which is the voltage leads the current. Does that make sense? Isn't inductor voltage supposed to be inductor voltage?
Oh gosh, that's so annoying.
Yes, the inductor's voltage is supposed to be omega L cosine the inductor's voltage.
Yeah, okay. See, if you plug in V, so what is this voltage here? Wait, actually, hold on. Oh wait, I see what you're saying. Yeah, this equation is, I took it from the wrong slide. Let me find the real equation real quick. Let's see. I think, oops. Wait. Ish. I think you're right. The equation, let me just double check. Actually, it's in my notes.
I have an equation sheet if you want to do a quick reference.
This is a bit weird. That's a good question. Let me look in the book. Wait, where was the, I can't see the chat for some reason. What was, can I see your chat, Steven?
Right here.
Oh my gosh, I don't, look, I pressed chat, I did. Look, I pressed chat and nothing happens, bro.
You see the triangle there? And let's do Alt tab.
No, I don't see the chat. Oh, what the hell? Okay, it's here now. So it should be the inductor voltage, you can say it as I times omega times L times cosine, okay? And that's equivalent to V times cosine, okay? So it should be V times cosine, Donovan. But there, I think you meant to write I times omega times L times cosine, right? Donovan. Okay. Because I'm pretty sure, yeah, this equation is correct. The voltage is equal to that. Okay, if you're still confused, wait. So the capacitance one, let me see. What did I write on here? I copied it from the book. Yeah, it's I. You're right, it is I. Yeah, it looks like a 1, but it's I, yeah. Okay. All right, we're gonna move on. Stu, can you make sure that if there's any other question,
Yeah.
because I can't see the chat, it's so annoying. Let's just do this question real quick. All right. So, okay, so this circuit right here, we're given the resistance, we're given the inductance, we're given the capacitance, and the question is asking us to find, well, we don't need to find everything, but let's just, okay, we can find the reactances really easily, right? It's just multiplying the omega for XL is omega times inductance, and XC is 1 divided by omega times capacitance, right? So just plugging in, and impedance, you just plug it in as well. Square root of R squared, blah, 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 blah. Okay, now let's look at the current. Oh my gosh, I can't see the question. Okay. The current amplitude, I. How do we find the current amplitude, I?
Wouldn't that just be voltage divided by resistance?
Okay, but what is the voltage? Do we, well, is it this voltage right here that you're talking about?
Yeah.
Yeah, that's right. And divided by what? What did you say?
By the given resistance.
Given the resistance. So you're talking about this resistance right here?
Yeah.
Remember, when we're talking about the RLC circuit, all 3 components combined, remember how when we had multiple resistors combined, we had to find the equivalent resistance? So basically like collapse, combine a bunch of resistors together. Well, it's kind of similar for the RLC circuit. We have to combine all 3 of these components together in order to find the total resistance. It's not really called the resistance, it's called the impedance. So actually how you find the current amplitude of this circuit is you do, remember, V equals I times impedance is the equation, right? So V in this case is 50, and I in this case is what we're trying to find, and Z is what we calculated right here. And Z is pretty easy to calculate. You just plug in directly XL, XC, and the resistances. Does that make sense, Domin?
Yeah, my bad. I wasn't fully paying attention. I forgot. Yeah, but I understand now.
Yeah,
Wait,
yeah,
I have a question.
yeah, sure.
So since this is an AC circuit, wouldn't you have to convert that V, which is assumed to be RMS value, to regular voltage? Or no?
Okay, what is it asking for? It's asking for the current amplitude, and what does it give us in the series? Okay, so I assume that this gave us the voltage amplitude. Hold on, let me just make sure that this is.
So yeah, on the
correct. You
test,
might
how
be
do we know for sure?
All right, let's see. Well,
Wait, it's asking for the voltage amplitude at the end of the question. So wouldn't you have to assume that
oh,
voltage is the VRMS, and then you
But
have to
that
convert
voltage amplitude is across each element, so that's different than the
across each
voltage.
element, yeah.
So I did a couple of practice problems, like just YouTube videos, and those weren't RMS. They just assumed that was the max.
Yeah, well,
I'm not sure.
yeah, that's what I assumed. I assumed that this was the max. When I was thinking about RMS, assuming RMS, I'm usually thinking about, like, you know, if they say that a wall outlet has a 120 volt,
Yeah,
you
then
know,
that's
120
RMS.
volt outlet, you don't say if it's RMS or not, but you assume that that is RMS. But in this question in particular, we're talking about all these things are amplitudes, so I'm assuming that this is also an amplitude. But let me see what the answer is. Oh my gosh, this thing is so annoying. Yeah, they assume that in the answer, they also assume that this was just the maximum voltage. So, you know, and what I would say, Ray, on the test is just assume that you're given what you need. And if you are doubting it, just give it your best shot. And if you get it wrong, just complain or just talk to Dr. Perez about it and explain to him your reasoning. He'll probably.
I think just assume everything is max voltage unless if it's a
Like-
household appliance.
Sure,
and
yeah.
walls.
Sure. I think that's a good benchmark to use.
Or if it says the RMS. Otherwise, assume it's max.
Mm-hmm. Okay. All right, well, all right, so where are we? All right, so now let's try to calculate the phase angle. How do we do that? Well, there's an equation for it, right? We're just gonna use the tangent theta is equal to XL minus XC divided by R, right? Everyone's familiar with this equation. It's probably on your formula sheets. Did I get that right? Yeah. So, and you're given all of them in this question, so you can just work it out yourself. Okay, now let's find the voltage amplitudes across each circuit element. Okay. So remember when you're talking about a circuit, so remember the loop rule in a circuit. If you go around a circuit, then all the voltage drops have to add up to 0, right? So basically, and it's also talking about the voltage amplitudes here. Okay, so we're not talking about sines or cosines. We're not talking about the oscillating version. I see a chat. I times yes, that is exactly what it's going to be, Tanner. So you found this I in this last problem, the current amplitude, and then you're just going to multiply by either the this reactance, or the resistance. So you can work that out by yourself and see what you get, and it should be. Let's just make sure that this is the right answer. Yeah, that should be right. Yep, that's right. Okay. Anyone have any questions about any of this stuff? Okay. Now let's move on to power dissipated. This is just a simple formula. It should be in your formula sheets. If not, just add it. Usually, I don't think you'll ever have an instance where it asks you for the instantaneous power. It might ask you for the power amplitude, but this is the power average. Okay, so the average power is just, as you can imagine, average is also just RMS. RMS just means average, kind of. So you're just multiplying. It's just like the classical definition of power is just VRMS times IRMS. All right, power dissipation. So what is this? What does power dissipation mean? Power dissipation, all right, so in an RLC circuit, the only component doing power dissipation is the resistor, right? So in this case, what we're calculating is the power dissipation by the resistor. Nothing else in the component does power dissipation. No, you don't need to do that. Energy, so I think the only time you need to worry about energy stored in the components is just in a pure RL circuit. Sorry, not RL, LC circuit where you have an oscillation. That's the only time you need to talk about energy. Otherwise, I think this is outside the scope of the class, talking about the energy of AAC oscillation with resistance. Okay. But if you come across a question about that, Tanner, you can just ask me and I will see if it really is outside the scope. Okay. All right, moving on. This is also a really simple concept. The resonance of an AC circuit. Okay, so what does resonance mean? Resonance means basically, remember how going all the way back to the definition of AC voltage, you have voltage is equal to the voltage amplitude times cosine omega t. And remember what omega means? Omega means the driving amplitude, driving frequency of the AC itself. And remember what Stephen was talking about. Stephen said that the resonance of a LC circuit is 1 over square root LC. So it makes sense that if you have the driving resonance equal to this resonance as well, then you're going to have the maximum voltage and current. And that's what resonance means. So like remember in our physics lab, you could see the curve of the resonance. You can see that it peaks out and then it drops down. So like it looks like a Gaussian almost. And that's the peak is where it's at resonance. It's where the driving amplitude is equal to this resonance value calculated from 1/√LC. Yes. So how do you know? Yeah. When reactances are equal, yes, I think you're right. When reactances are equal, you have, wait, I think it might be a bit different than that. Oh no, you're right, yeah. When reactances are equal, you have resonance. And the reason, if you're curious, the reason why when the reactances are equal, remember that the current the definition of current current is equal to, well actually, whoops, Zi is equal to voltage, right? So that means I is equal to V over Z, which is V over square root R squared. Plus XL minus XC squared, right? That's the definition of impedance and stuff. When XL is equal to XC, you can see in this case where XL is equal to XC, this thing becomes 0. And this is actually the smallest that this denominator is going to get, which means that this is going to be the biggest. And that's when resonance happens, because resonance is defined as maximizing voltage or current. Actually, technically it's current because voltage is a constant. You apply the constant alternating voltage. Okay, any other questions? Because this is actually the last slide in our this presentation. So after this, if anyone else has any questions about anything, you can ask it, or if you guys have specific topics that you want to go more in depth in.
You're reading the chat?
Yeah, I think so at least. Okay, all right, so if no one has any questions, then we'll hang out for like maybe 5 more minutes or so. Thank you, Ellie. We'll hang out for like 5 more minutes, and you guys can feel free to leave now. And anyone else who might have one pop up, you can just talk on the chat. But thank you guys for coming, and good luck on the test tomorrow. Bro.
Thank you, guys.
All right. Krithika, what do you mean recover stuff? Oh, sorry.
Covered again.
Recover.
Sorry.
Okay, yeah.
Yeah.
Stuff
So,
on. Yeah.
yeah, I think there was like an XRT thing. I can't remember. It was on like the last one, the one that was due like Monday. I think the LC oscillators one. It was like, what's the charge on the capacitor? Wait, hang on. Let me see if I can log in and get you the question.
Okay. What is the charge? Oh yeah. Get the exact question and go. I think you can either send it to me, or you can actually even post it on your screen, or share your screen rather.
I'm on a different device right now. Sorry, but
Yeah,
okay,
that's
so the
fine.
question is like, they give you the voltage, the capacitance, and the inductance, I think.
Mhm.
And they're like, what is the maximum charge in the capacitor during the oscillations?
Okay. Yeah, here, let me get a whiteboard. So basically, you have a DC voltage, right?
Mm-hmm.
And then you have a inductor and you have a capacitor. And you're given the inductance and you're given the capacitance and you're given the voltage, right?
Yeah.
And you're asked for what is the charge or the max charge on the
Mm-hmm.
oh wait, I drew this backwards, huh? This should be C and this should be on the capacitor. Okay, well, let me start off by asking you, how do you find the charge on a capacitor?
Oh, good heavens, I have no idea. Wait.
You look at a formula sheet. We cover this in the capacitor chapter.
Yeah, okay, that's not my current formula. Formula sheet only has like the student.
Yeah.
I forgot.
Well, that's fine. I'll just tell you what the equation is. The
Okay.
equation for charge is equal to CV, okay? So the capacitance times the voltage, okay?
Oh, that's it?
Yeah, that's it.
Goodness.
But all right, however, we gotta be a bit careful because remember it's, what this guy does? This guy oscillates, right?
Mm-hmm.
Wait, hold on. What's the exact question? Because normally in a LC oscillator, you won't have a voltage guy here. This is just to charge it initially. Is it?
Charge it initially? What is the max charge initially, basically?
Was that what it's asking? What is the max charge initially?
Yeah, what's the max charge?
Okay, well, yeah, you would just use this equation.
Yeah,
The capacitance
okay.
times the
Yeah.
voltage. I thought it was going to be, once it starts oscillating, what is going to be the max charge. And it's actually going to be the exact same answer because energy is conserved.
Yeah, it's true.
Okay, cool. Anyone have any other questions?
Wait, is the test at 3? I forgot. Is it 3 or 4?
I have no idea. Wait, when's the test, Steven?
I have no idea.
Yeah, okay, this is not what we're trying to tutor here.
I know, you're good.
It would be helpful to know though.
It would be definitely helpful. Does anyone know when it is?
I'm texting the group chat. Let's see if that
Okay,
helps.
cool. 3. Cool.
So it's like
Oh wait, he's giving us 1 extra hour, right? To sub.
Oh yeah, I think you can like start like late or something.
Wait, what? What'd you say?
You can like start late. Like you don't have to start right at 3 or something. That's how it was last time. Like I started like 10 minutes late. But I started like full time or whatever.
Okay, cool.
Yeah, someone just said in the group chat it's 3 to 5:50. That's what it was last time.
All right, sounds good. All right, if anyone has any more questions, I think you guys can just message us separately. Okay, I'm going to end the meeting now, okay?